Probably no need to write this down because we've talked about this, right? Quadratic function is something that can be of the form some number times x squared plus a number times x plus a third number. And that's a quadratic function as long as a, b, and c are real numbers and a is not equal to 0. If a is 0, x squared is gone and we've just got a line. Make sense? So we know that when a is bigger than 1, it opens up, and when a is less than 1, it opens down, right? And nothing new and special there. The only thing that we didn't talk about last chapter was the axis of symmetry. And because these are all x squareds opening up, not y squareds opening to the side, we are always dealing with x equals whatever the x coordinate of the vertice or vertex is for your axis of symmetry. All that means is it's a mirror reflection, right? Everything opens up to either side perfectly, so it looks like a mirror. Okay? Any questions on this slide? All right, so this is what our book calls the standard form of a quadratic equation. It was known as vertex form in our Algebra 2 books. So f of x is equal to a times the quantity x minus h squared plus k. When you get a quadratic in this form, x equals the h component is going to be your axis of symmetry. Your vertex will be at hk. Notice it was x minus h, so it's the opposite sign of whatever is with the x, and the k does not change sign because it's shifting it left or right h and up or down k. When a is positive, it opens upward. When a is negative, it opens downward. And of course, when a is bigger than 1, it's going to stretch it vertically. When a is between 0 and negative, or 0 and 1, it's going to shrink it vertically. All those things we talked about last chapter. So our goal today will be to get it in that form so that we can quickly graph it and we can figure out what the intercepts are, the zeros. Okay, here we go. So first of all, let's do a little reminding of ourselves of what a perfect square trinomial is. Okay, these are called perfect square trinomials. Does anybody know why they're called perfect square trinomials? What do you think, John? Good. Both of the factors are the same number. Do you see this perfect square here? 25. If I factor this, I will get what? 5 and 5, and the signs are both positive. So it could be written as x plus 5 quantity squared, a binomial squared. Okay? That looks suspiciously familiar, because if we have something that says f of x equals something plus k, maybe with an a out in front, do you see that this is our x component of our h of our vertex? Okay, we'd have to bring it to the other side to get a -5, but we'd be in good shape. Does that make sense? Okay. How does x squared minus 4x plus 4 factor? Yep, x minus 2 quantity squared. And how does x squared minus 6x plus 9 factor? Yeah, x minus 3 quantity squared. So our goal is going to be to get some of these perfect square trinomials so we can write it as a binomial squared to get it in what our book calls standard form or vertex form from our old book. Make sense? All right, 2 ways that you can do this. Okay, you can decide that you're going to leave this guy on the same side but just move him out of the way and think about him in a little bit, or you can move him to the other side of the equation. Okay, so let's start by writing this as y equals, and this is really x squared plus 6x minus 1. So if you want to move that 1 to the other side so you don't have to be confused by it, you can bring it to the other side. It will be a positive 1. And then we have an x squared plus 6x over here. So we want to make this a perfect square trinomial. To do that, we need to add something that will make it so it's x plus something quantity squared. So what number are we going to add to this side? 9, exactly. So if we add 9 to this side, I should have given myself some more room here. That means I have to balance my equation by adding 9 to this side. And it doesn't hurt to have a different color pen or pencil or something to help keep these straight. Okay, so this is y plus 10 now. And we made our perfect square trinomial. What is this squared? Right. Okay. So how I do this is I ask myself, what is half the middle term squared? Half of 6 was 3. 3 squared is 9. That's why we added 9 to it, to make a perfect square trinomial. Okay? And now the only thing we have to do is to get it back into its regular shape, or regular form, its vertex form, or standard form in our book, by bringing that 10 to the other side, and we can say x plus 3 quantity squared minus 10 now. Because on the right side it will subtract 10. Had you decided to leave that minus 1 on one side, you could have said, I have y equals x squared plus 6x. I'm going to leave this minus 1 hanging out over here. Half of 6 is still 3. 3 squared is 9, right? So if I add 9 to complete the square, I have to subtract 9 from the same side of the equation, not 10, 9. I was doing the math in my head, so that I don't unbalance it. Does that make sense? Okay, so you choose whether you bring your constant to the one side and add to both sides, or if you keep everything on one side, but make sure that you balance it by subtracting whatever you add or adding whatever you subtract. Does that make sense? You get the same result either way. You just decide which one works better for you. Okay, so we found it in standard form, vertex form. What is the vertex of this parabola? -3, -10, because our h is 3, so x minus 3, right? Or plus 3 means I have to bring that 3 to the other side. H becomes -3, and k is -10. So -3, -10 is our vertex. And you'll get tired of writing the axis of symmetry because there's not a lot of change here. So it's always a parabola opening up or down. X is always the one that's squared. But what will our axis of symmetry be? Not just -3. That's just a number, but a line. What's the line? That's the axis of symmetry. X equals -3. So there are the two answers that we're looking for. Everybody remember this? Okay. Done it before. It's been a while. All right, what questions do you have on this slide? Yes. Why is the x-axis part of this? So when we think about this, this is now a parabola opening up, right, with a vertex at 3, -10. So if we sketch this, we are at 3 over, shifted 10 down. We have a vertex here, and we said it was opening up, right? So if I move 1 step to the right, what's 1 squared? And 1 step to the left, -1 squared. Okay, now I move 2 steps to the right, what's 2 squared? So when I move 2 steps to the right, I have to go 4 up. And 2 steps to the left, 4 up. So, and then 3 would be 9, right? It's going to look something like that. So do you see that this is opening equally across that line? It's a reflection, a mirror image. And what is that line? That's the line of x equals 3 the whole way. Okay, it's got to split off evenly on both sides. Make sense? Okay, because if we took the time to actually plug in 4 and 2, we will get 9, right? And then if we took the time to plug in 5 and 1, we would actually get negative 1, 2, 3, 4, 5, 6, okay, and so on. But this is much faster than plug and chug, plugging in numbers. Okay, so it's a little tougher, but not too crazy. Okay. So now we want to know what the x-intercepts of this function are. Okay. When we're talking about x-intercepts, go back for just a second. We're trying to figure out what are the zeros. Where is this guy crossing the x-axis? In those 2 spots, that's where y is equal to 0, right? Make sense? Okay. So if we have something already in vertex form, it helps us to find out where y equals 0. Because this vertex, or standard form as our new book calls it, is y equals x plus 3 quantity squared minus 10. And we want the intercepts, the x-intercepts, the zeros. So what do? Yeah, set it equal to 0. 0 equals x plus 3 squared minus 10. So I bring the 10 to the other side to try to isolate x, and a positive 10 is equal to x plus 3 quantity squared. And then how do I get rid of a squared term? Square root, okay? So this is where we have to make sure that we're introducing our plus and minus, because there are 2 values that will do the trick, one positive and one negative. So when we take the square root of both sides, our x plus 3 will be equal to plus or minus square root of 10. I just took the square root of both sides. So we're almost home. Now it's simply a matter of getting the x by itself. So we'll have a negative 3 plus or minus the square root of 10. And you can write it in that form. And if you prefer to say negative 3 plus or minus the square root of 10, 0, that's even better because those are the actual intercepts. It's written as the 2 ordered pairs in combined form. Make sense? Okay. So what is negative 3 plus the square root of 10? Square root of 10 is a little bit more than 3, right? So negative 3 plus a little more than 3. Yeah, going to be little, kind of point something. So that just means that we had a vertex at negative 3 and down here at negative 10. And then we have our intercepts at a little bit more than 0, right? And then what would be -3 minus the square root of 10? A little bit less than 6, right? So it wasn't going to be nice, neat numbers. But if I graph it with a lovely graphing calculator app, we can see that it's -6.162 and 0.162. Okay, gives us a more accurate picture. And here's that spot where we were 1 away, 1 up, 2 away, and 4 up, right? 3 away from our original, and 9 up. See how it's opening beautifully around that axis of symmetry? Yes, sir. To get the -3, -10, it's in vertex form. So when we see that, we say, okay, h is going to be -3, and k is going to be -10. We always change the sign of this one, but keep that one the same. Okay. Other questions that you have on this one? Make sense? Okay. All right. Had you wanted to, you could have, you know, we completed the square to get this in this form, right? But we could have gone back and said, hey, I've got this original function, right? I know I can't factor it, can I? So there are no factors of -1 that subtract to get 6, right? So then we would have to put it in quadratic formula. So that is another way to get your intercepts. You have it in this original form, plug it into the quadratic formula if it doesn't factor, and you can find your intercepts. Does that make sense? But once it's complete, the square has been completed, it's very easy to bring the 10 over and then square root and then bring the 3. All right, next example. What happens when a is not equal to 1? So our next example says find the vertex and axis of -2 times x squared minus 4x plus 1. So we change it up by simply writing y equals -2x squared minus 4x. Did you prefer to see the 1 with the y, or to leave it over here and add and subtract? Other side? Okay, so we're going to take that 1 to the other side, and it's now a -1. Okay, I think it's less confusing if you bring it to the one side, but some of you can do it without. Okay, now, this isn't as easy to find a perfect square trinomial for, is it? Okay, because it's got this -2 hanging out. So if we factor that -2 away, it's like dividing everybody by -2. We have x squared plus 2x. Agree? Okay. Now we say, what is 1, wrote it down wrong, 1/2 the middle term, or what was the middle term, squared. Half of 2 is 1 squared is, so we're adding 1, but not really. Because distributive property says this -2 should really be written multiplied by that 1, right? So what is -2 times 1? -2. So we truly added -2 to the right side. To balance it, we're going to have to add -2 to the left side. Make sense? Okay, so we're taking away 2 from this side. Half of 2 is 1, 1 squared is 1, but the net result was negative 2 times this. We've added negative 2 to the right side. So we add negative 2 to this side, and now we get negative 3 because there was a negative 1 there. Yes, Phil? The negative 2 came from the fact that we have not a nice x squared here, is it? So how do we get that x squared away, or that negative 2 away? We have to factor it out. So we took it out and we divided this by negative 2 and this by negative 2. And they went there. Okay. So far so good? Haven't lost anybody? Okay, so here we go. Now we have y minus 3 equals negative 2 times this perfect square trinomial that we designed by choice by taking half the middle term squared. What does this factor into? X plus 1 quantity squared. We did that so we could get the x value of the vertex, the h. Okay. Bring the 3 back over, and we've got what our book calls standard form. It's now a positive 3 on the right side. So what is our vertex? Negative 1, positive 3. Because it's x minus h. Okay, and then you keep the sign of the k. So there's our vertex. Okay, what's our axis? Axis is a line. The line is x equals negative 1. That's going to get boring. After you write the vertex, you're going to always write x equals and then whatever the h value is. Okay, nothing to change up until later when we talk about parabolas that open to the side, the y squareds. Okay. Shall we find the intercepts? Practice that? Okay. When it's in this form, it's nice because we set y equal to 0. And so if we have 0 equals this negative 2 times x plus 1 squared plus 3, that means we're going to take the 3 to the other side first. So we'll have a negative 3 is a negative 2 times the quantity x plus 1 squared. And then how do we get this 2 away? Divide. So we divide by negative 2. And it's probably good to leave it as a fraction. Almost there. 2 more steps. Because it's squared and then we have to deal with that 1. So the opposite of squaring is square root. But if we square root, we have to remember to include our plus or minus here, right? So we'll have plus or minus the square root of 3 over 2. And then we have to bring our 1 back because we want the x all by itself. So when the 1 comes to the other side, it will be a negative 1 plus or minus the square root of 3 over 2. But we drilled it into you last year. What don't we like about that answer? Radical in the denominator. Has a fraction with a radical in the denominator. How do we get rid of that 2 in the denominator? How do we rationalize it? Times the top and bottom by 2, right? So that gives me a perfect square down there. What is the square root of 2? Square root of 4, 2. So we'll have negative 1 plus or minus the square root of 6 over 2 is our x, and then of course our y will be 0. Okay. What questions do you have on this one? I want that extra step to find the vertices. Of course, you could have plugged this into quadratic formula to get the vertices as well. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Everybody remember that? Anybody have to sing the Pop Goes the Weasel song with it? Anybody never heard the Pop Goes the Weasel song with it? All right, here we go. One more to practice. Make sure we got this down. A is not 1 again, so we have to deal with that 2, that leading coefficient of 2. So let's write this as y minus 1 to bring the 1 to the other side. And we have a 2x squared minus x. So we want to take that 2 out. And when we factor that 2 out, we will have x squared. So if I divide this by 2, I get x squared. What happens if I divide negative x by 2? Negative 1/2. Okay, that's going to be our middle term. So now think about what is 1/2 of 1/2. 1/4. We want to take 1/4 and square it. So 1/4 squared is 1/16. But did we really add 1/16 to this side? How much did we add? 1/8, right? Because 1/16 times 2, the 2 and the 16 cancel, we get 1/8. So we have to add 1/8 to this side. So we got to work with some fractions. So now we have a perfect square trinomial over here. X minus what? Quantity squared. 1/4. Just take the square root of your third term. Okay. And negative 1 is how many eighths? So negative 8/8 plus 1 more eighth gets me negative 7/8. If it was negative 7/8 on this side, I'm going to skip a step and I'm going to write it as a positive 7/8 on this side. Is everybody okay with that? This net result is negative 7/8. So coming over there, it's going to be a positive 7/8. Okay. Now we can find the vertex. Vertex is a point. What is that point? Positive 1/4, 7/8. We changed the sign of this one, but not that one. Okay. And our axis, x equals 1/4. We know it's opening up, right? And we know that it is going to be steeper. It's going to stretch it vertically. And we won't necessarily have to graph it. Okay. Vertices, you could plug this into quadratic formula because, again, I don't believe it's going to factor. It might, but I'm doubting it. Or we could try to factor this guy. All right, what questions do you have on these? All right, Dylan's getting ready to go to sleep on me, so we got to get one more in here. It's hard. It's easy to nod off. Anybody want to stand up and stretch? Get out of your seat for a moment? Feel free. I'm used to walking around all summer long, and then I get into the classroom, and I get to walk, and you guys have to sit, and that's not fair. So stand up, stretch. Make the blood flow again. It's all been pooling in our butts, so we got to get it up and get it in our brain again. All right, last one. This one actually requires a little bit of brain power, so we have to think this through. So we have a standard form of an equation of a parabola with a vertex at 1, -2, passing through 3, 6. So our book calls standard form y equals a times x minus h squared plus k. All right, so we know the vertex, right? Everyone see that vertex? So we have most of this, don't we? We don't know what A is necessarily, but we do know that H is this 1, right? So it's going to be minus 1 squared, and then plus negative 2. Or if it makes you feel better to write minus 2, by all means do that. Okay, we change the sign of the H, and we leave the K the same sign. All right, so that's looking pretty good. What do we have to find? A. How are we going to find it? I like where you're going with that. Could we use the slope formula? Slope formula is for lines, right? To find the rate of change. And this is a rate of change. You can equate it to that. It could, if it makes it steeper, if it's bigger than 1, right? Because it's stretching it vertically, and it flattens it if it is. So there's nothing wrong with thinking in that way. But do we have a, go ahead. Yeah, let's plug in 3 and 6, right? Because we have an x and a y, don't we? And all we're missing is this a. So we'll plug in this 6 for y. And the x is a 3. Okay, so we're subbing everybody in. And then order of operations says we have to do our subtraction in the parentheses first. So 3 minus 1 is, and 2 squared is. So we have 4a minus 2 is equal to 6. So now what? Add 2. 8 equals 4a. So what does a happen to be? Yep. So plugging it back in, we plug it into this guy, and y equals 2 times the quantity x minus 1 squared minus 2 is our standard form, as this book calls it, of an equation, of a parabola, with a vertex of 1, negative 2 passing through 3, 6. Okay, what questions do you have about this one? Okay. All right, let's talk about min and max, and we're done. Okay, so we talked about relative mins and maxes last chapter, right? We wanted to know, what's that peak? What's that turning point? Okay, where is this thing changing directions, going from increasing to decreasing, or from decreasing to increasing? Okay, that's nothing more than the vertex, is it? So we have the height in feet of a ball thrown by a child, given by the equation y equals negative 1/8 x squared plus x plus 4, where x is the horizontal distance in feet from where the ball is thrown. How high is the ball when it's at its maximum height? Trying to find this peak. What do you think, Phil? Okay. So we're trying to find that peak, right? We gave you a shortcut last year. We're going to remind you of that shortcut. If you find negative b over 2a, you get the x value of that min or max. So you don't have to spend time completing the square on this guy to figure out what the x value of that max is. Does that make sense? Okay, because it will be something like a times x minus h squared plus k if we do complete the square on it, and this h will be the opposite of h will be your maximum height, right? But that can be found by simply taking negative b over 2a. So which of these guys is b? This is in the other form now, right? The one is, so here's your a, here's your b, and here's your c, right? So we're going to change the sign of b and then put it over 2 times a. So So we're taking that over 2 times a negative 1/8. So first of all, let's simplify this. There's a 2 in the numerator, 8 in the denominator. It reduces to 1/4. So I have negative 1 over negative 1/4. How do I get rid of a fraction over a fraction? Times it by its reciprocal, right? Okay, so if we're multiplying this by its reciprocal, those guys will cancel, won't they? The net result is simply invert and multiply. So what is a negative 1 times a negative 4? 4. 4 is the x value at that height, or at that, so basically it's that time. Okay? So now they want to know, okay, this is 4, right? In our parabola, they want to know this, don't they? What is this guy? Y. So what do we have to do? Plug in 4 everywhere we see x. Does that make sense? So we can complete the square and still get it to find out what that y is, okay? To find out that k. But it's a lot easier to find negative b over 2a and then plug that number in. So when we put 4 in, we will have negative 1/8 times 4 squared plus 4 plus 4 more. Everywhere we see x, we put in 4. Okay? What is 4 squared? 16 divided by 8? 2. So we'll have a negative 2. And I was putting my finger up there so it drew all over the place. Negative 2. And then we are adding 8 more. So we get 6. And this is feet. All right. Questions you have about this one? Yes, sir. Okay. So this point, this ordered pair here is the point where x was 4 and y was 6, right? So we were looking for the maximum height, how high the ball is when it's at its maximum. We were just looking for the y-coordinate. But it happened 4 seconds after he threw it. Does that make sense? And the ball was in play for a total of 8 seconds because this is the axis of symmetry. It started here and ended here. Okay? Now, one slight thing. The child, we don't know how tall he is, right? I think that was already taken care of. Okay? So we won't know necessarily where it hits the ground. Okay? Or how much longer it takes. Because this is just the arc from his arm, however high that arm was when it released, to where it hits that same height later. Okay? Very good? All right. Assignment.